Last year, I created this. It's a portable laser device designed to project text onto distant surfaces like walls. The goal was to achieve a range far beyond that of a typical projector, albeit with a major trade-off in resolution. The device uses a rotating array of 12 mirrors, each set at a slightly different angle to generate scan lines. Meanwhile, the laser turns rapidly on and off within those lines to form pixels. Although it worked fairly well, I felt that there was significant potential for further development and expansion of this concept. To make a better version, there were a few key things that I needed to tackle. First up, the resolution. Vertically, it was limited to just 12 lines, one for each mirror. Horizontally, I could display about 20 characters, each with roughly 8 pixels in them. This was due to a mix of the Arduino's limited clock speed and my less than perfect code. Then there was the horizontal wobbling effect. While some viewers thought that it looked cool, it wasn't exactly what I was going for, and it did make the text harder to read. Another issue was that the device only projected in green and didn't have any brightness control. The laser was either on or off. The power source was also an area for improvement. I used 8 AA batteries, which was a bit bulky. A rechargeable lithium-ion battery would have been more compact and efficient. Lastly, the device only handled static text input via USB or Bluetooth. But before we go any further, what am I really trying to accomplish here? Basically, I want to be able to project not only text, but also simple graphics, animations, and maybe even low-resolution video over long distances. To do that, I need to create raster images, meaning ones composed of individual pixels rather than just lines. Most existing laser show projectors don't do that. They produce vector images composed of connected line segments. The advantage of raster images is that they can show filled-in areas instead of just outlines. You can almost think of this device as trying to recreate mechanically what a CRT TV does electronically, except with lasers instead of an electron beam. I want to take a quick second to remind everyone that experimenting with high-powered lasers can be extremely detrimental to your eyesight, so if you're going to mess around with this kind of stuff, make sure you know what you're doing. To begin with, I decided to see if I could just improve the existing device. The first step was to overhaul the code. From the comments that I got on the first video, I learned several helpful tricks to help streamline things. I also revamped the character data arrays to use 8x12 pixel grids of ones and zeros, representing on and off states, much cleaner than the previous system that used positive and negative numbers. Ultimately, I was still bottlenecked by the Arduino Nano's clock speed, 16 MHz. So I decided that it was time for an upgrade. Enter the Teensy 4.0, which has a 600 MHz processor. That's 37.5 times faster. It also has more pins, greater flash memory, and some other nice features. But it is a 3.3 volt system, so I had to make some adjustments. I updated the circuit board to fit the Teensy, and combined with the improved code, this made a noticeable step up in the quality of the projected image. But these improvements were really just fixing issues with the existing device. I wanted to see how far I could take this concept. The single most obvious upgrade was to improve the resolution, mainly because I wanted to do more than just project text. The advantage of my original setup was its simplicity. There's only one moving part, the mirror array. However, each line requires a mirror, and the more mirrors that you add, the narrower the horizontal line becomes. That's because the maximum scan angle is 720 divided by x, where x is the number of mirrors. So, more vertical resolution means less horizontal resolution. There's also the fact that just getting 12 mirrors aligned was a huge pain, so I don't even want to think about trying to adjust several times that many. I guess it would be possible to machine the whole thing out of a solid block of aluminum and polish the sides into mirrors, but unfortunately, I don't have the ability to make anything that precise here at home. Another idea is to add more lasers, but that would significantly increase the cost, take up more space, and make alignment even more of a hassle. So how do we improve the resolution? My solution was to combine a spinning polygon mirror for the horizontal scanning with a secondary mirror that adjusts the vertical angle. But why not just use a dual galvanometer setup like every other laser projector? In a word, horizontal scan speed. I guess that's 3 words. But anyway, the thing about galvos is that in order to move to any position, they have to accelerate, move, slow down, and stop. The further they have to move, the longer it takes. Now, don't get me wrong, they do this all incredibly quickly, way faster than you can blink, but not instantly because of inertia. The polygon mirror, which rotates continuously at a constant rate, doesn't have to worry about that. But then you might ask, how is it possible to use a galvo for the vertical axis? Well, for this device, remember that the aim is to display a rasterized image. So the distance between the individual scan lines is really small, and therefore the galvo can move there very fast. Because we're only trying to produce a single horizontal line, we can cheat a little bit and use an existing part for that. A laser printer mirror. It's still got 12 mirrors, but they're all at the same angle, unlike what I built before. The mirrors are pretty small, but just big enough to reflect the laser beam. Getting it to work wasn't too hard. It just needed a 24-volt power supply and a PWM signal applied to the right pin of the control chip. I did have to get a little bit creative here and solder a wire straight onto the PCB, because the speed control wasn't working quite the way I expected out of the box. I decided to use essentially the same timing system as the first version. 2 IR sensors and a ring of 3D printed tabs to trigger when each mirror was about to pass in front of the laser.
There's probably better ways to get the mirrors positioned, but this is just what I could get working reliably.
Now, let's turn to the vertical axis. I picked up a set of galvos from eBay rated at 50k PPS, which is a measure of their speed. They came with a driver board and a power supply. Specifically, a power supply capable of producing both positive and negative 24 volts, necessary for their operation. Unfortunately, this adds some complexity, which I'll touch on a bit later. Controlling these galvos is as simple as producing a voltage signal between -5 and 5 volts, though in practice you can just use 0 to 5 volts, which will just give you half of the deflection angle range.
To generate specific voltages, I used a digital to analog converter, or DAC.
The MCP4822. It's a budget-friendly 12-bit SPI chip in a DIP package, making it perfect for breadboard experiments. It has 2 channels, so you can technically control 2 galvos, but for this project, we only need 1. Here's how it all comes together. The laser beam exits the diode, passes through a focusing lens, hits the spinning polygon mirror, reflects off of it, then strikes the galvo mirror, and finally projects onto the target surface. Meanwhile, the laser is pulsed rapidly at specific intervals to form an image. Because the galvo does have to move back and forth, I wrote the code in such a way that on its way down, all of the even numbered lines are drawn, starting with 0, and on the way back up, all of the odd numbered lines are drawn. This whole process has to happen many times per second.
The main limitation is the maximum RPM of the motor. Here's the math.
Frame rate is equal to the number of mirrors times the motor's revolutions per second divided by the vertical resolution. So in short, doubling the vertical resolution halves the refresh rate.
With the theory figured out and the basic parts in hand, I set out to build a working prototype.
I started out using a blue laser diode for testing since I already had one lying around, and I didn't really want to take apart my first projector. To keep everything secure, I 3D printed a base to hold the laser housing next to the motor. I also incorporated an outer shell to prevent any dangerous stray reflections. This also held my prototype circuit board on top like a kind of lid. Then I had to rewrite the code to synchronize the movement of the galvo with the timing of the spinning motors. I maintained the 8x12 pixel grid setup from the first version and adapted them for use with the galvo. As you can see, the improvement in visual quality is already pretty big, even with minimal effort being put into the horizontal alignment. You'll notice occasional glitches where the timing system misfires and random lines get projected at the wrong time. I haven't pinpointed the exact cause, but I suspect it's some kind of EM interference on the phototransistor wires. I did switch back to using a green laser here, but I wasn't quite ready to add multiple colors yet or mess with brightness control. I gradually increased the number of lines and adjusted the motor speed to find the right balance between resolution and refresh rate. Here's an early test of a 48x48 checkerboard image. Ultimately, pushing beyond 120 lines of resolution proved challenging. Beyond that, the strobing effect started getting unpleasant.
Now's a good time to mention another one of the problems that I had to deal with: the beam profile.
Take a look at these 2 images. Both are displaying the same picture using the same laser. You'll notice that the one on the left looks very blocky and pixelated, but has nice sharp edges, while the one on the right looks more like something you'd see if you looked closely at an old CRT TV.
The difference here is merely that I rotated the housing. See, unfortunately, the beam is not quite round.
Actually, the spot it makes on the wall is more like a rectangle. So if I turn it vertically in relation to the mirrors, you get the image on the left. Taller scan lines with no space in between, and very sharp edges. But if I turn it horizontal, you get the image on the right. To a certain extent, it comes down to personal preference.
While I do think that the image on the left with the sharp edges is a little bit more appealing, unfortunately it requires more space between the lines, which causes the overall image to be larger and therefore reduces the maximum projection distance. So I opted for the horizontal orientation.
Now, the number one comment that I got on the first video was something along the lines of, make it full color, or give it RGB, or something like that.
And I totally agree. Here's how that works.
3 laser beams, red, green, and blue, need to combine into one single overlapping beam using dichroic mirrors. These mirrors let certain colors pass through while reflecting others.
Initially, I planned to build my own setup, but after struggling to find the right diodes and get everything aligned, I decided to just buy one online.
By simply turning each of these lasers on and off, you get a palette of 7 colors. 8 if you count all of them being turned off as black.
In order to have full control over what color the light is, you actually need some kind of driver that allows you to vary the output of each diode.
Now, normally, if you wanted to color mix, say, 3 LEDs, you could just use pulse width modulation, basically varying the duty cycle of each color to achieve the desired mix. And this works because the human eye can't really tell that they are blinking at high speed. But because of the fact that this is a persistence of vision device, turning them on and off would simply result in a dashed line.
So what I really need is some kind of driver that can produce a consistent yet controllable brightness level, commonly referred to as an analog driver.
These are typically controlled via a voltage reference provided by a DAC. I found some promising schematics online and decided to build one. This is the basic configuration. It uses an op-amp and current sense resistor to rapidly adjust the feedback on a MOSFET. This actually works really well, and with a fast enough op-amp it can change the brightness very quickly. The real bottleneck I ran into was the DAC. To make a long story short, everything I tried was way too slow. I tested a self-built R2R ladder, the aforementioned MCP4822, and a couple of other chips, with no luck. The problem was that I needed the voltage to stabilize within 100 nanoseconds or less to achieve the right pixel size. I'm sure there's something out there that would work, but because I was trying to prototype everything on a breadboard, I was limited to through-hole components.
Now, believe me when I say that I really wanted this to work. In fact, I spent more than a month on just this aspect of the project alone. But at a certain point, you do have to say enough is enough in the interest of actually getting the thing done. So I reluctantly decided to go with simple digital driver circuitry. For now, anyway.
Now, let's take a look at the laser module itself. If we take the cover off, you'll see a solid aluminum block housing 4 laser diodes. 2 red, 1 green, and 1 blue. The dual red diodes compensate for their weaker output. Each laser points at a dichroic mirror, which lets specific wavelengths pass while reflecting others. The laser module also came with a driver board, but we're not going to use that because it sucks.
To be more specific, it can't switch the laser on and off even remotely fast enough. Luckily, now that I had decided to go with simpler circuitry, there wasn't really that much to figure out.
I just needed to multiply my existing design by 3 and tell the program which lasers needed to be on at the appropriate time.
Now, how do we turn the image into a format that the microcontroller can read?
Well, that's where this handy little script that I wrote comes in. This takes a GIF image or animation and breaks it up into frames. For each frame, it looks at every pixel from left to right, line by line. If the pixel is closest to red, it's assigned the value 1. If it's closest to green, it's assigned 2, and so on and so forth for the 8 possible colors. This process is similar to the posterize effect in Photoshop, reducing the color detail but making it usable for the driver board. With all of the pixel values defined, the script spits out a 2D array for each frame, which my Arduino program reads from an external file. As you can see from this incredibly janky setup, everything up to this point was totally hacked together and basically secured with superglue and kept alive by thoughts and prayers. Furthermore, I needed 3 separate power supplies just to run the thing. One for the motor, one for the galvos, and one for the lasers themselves. Not exactly the optimal setup.
In addition to putting everything in a nice compact footprint, I also wanted to make this thing portable. That meant battery power.
I was trying to think what type I could use that would provide enough juice. Then one day, while trying to do yard work, it hit me. My string trimmer has a 24-volt battery capable of driving a pretty beefy motor. So I cut some pieces of copper pipe brackets into electrodes and flattened them out with a hammer. Then I soldered on some wires. This gave me a 24-volt output, which I connected to a 24 to 9-volt step-down converter. That would be used to power the laser driver board.
Everything seemed to work. The only problem was I couldn't use it to directly power the galvos since that required both positive and negative 24 volts.
After doing some research online, I found this DC to DC converter component that takes in 9 to 36 volts and outputs positive and negative 24 volts. It was a bit pricey, but I needed something that could pump out at least an amp, and this fits the bill.
So now I had a fully functional, portable, in theory at least, laser projector.
But so far, it was still just a tangled mess of wires and disjointed components sprawled across the better part of my workbench. Time to clean everything up and put it into a sleek, user-friendly package. Step 1 was to swap this clunky prototype board out for something a little bit more professional. I fired up KiCad, a free PCB design program, and got to work. And here's what I came up with. You'll notice that I used some pretty big heat sinks on the LM317s. Technically, for this project, that's overkill. The lasers are never on for more than a few microseconds at a time, so heat doesn't really get much of a chance to build up. But in the event that they do get stuck on for whatever reason, I want to make sure that those parts don't just burn up.
I also like the idea of being able to use this as a more conventional laser show controller, so I decided to add a few extra features.
Like these potentiometers. They allow me to control different aspects of the projected image without reprogramming the device.
With the design figured out, I uploaded my files to my favorite PCB manufacturer, PCBWay.
They offer custom PCB fabrication and make it super easy to pick out how you want your boards made. You can choose the base material type, thickness, color, surface finish, and a lot more options. But that's not all. They also offer multiple types of 3D printing, injection molding, sheet metal fabrication, and CNC machining. The Instant Quote tool makes it super easy to get a price by simply uploading your files. Here's the PCBs I ordered for this project. I'm really happy with how these turned out. And speaking of CNC machining, I also needed a couple of aluminum plates to build the enclosure for this device, so I got PCBWay to make those for me as well, and they came out amazing.
Now, as far as the physical design of this projector, I wanted to keep everything as compact as possible, but I did have to jam a lot of bulky and unusually shaped components into a fairly tight space. The battery in particular was a bit chunky.
Basically, everything is bolted to the bottom aluminum plate, which is 1/4 of an inch thick. That provides a really solid foundation that keeps things from coming out of alignment. Internal components that require spacing or support utilize 3D printed parts. I made the walls out of wood, which I sanded, stained, and varnished. The front has a square aperture that lets laser light shine through, and in the back are holes for the Teensy's USB port and the potentiometer adjustment screws. On top of that goes the lid, made from an 1/8 inch thick aluminum plate. It has a nice big lighted power button right in the center that switches everything on.
First, let's kick things off with some indoor tests at a distance of about 25 feet.
What you're seeing here is a projected resolution of 180 by 120 pixels. As I mentioned earlier, the main limitation is the vertical resolution. The more lines, the slower the frame rate. Technically, I could push beyond 120 lines, but at that point it starts getting unwatchable. The horizontal resolution is more forgiving. I was able to comfortably reach about 320 pixels before the image started to get clipped due to the mirror width. Of course, lower resolutions work fine too, with the added bonus of a much faster refresh rate. You might have noticed the color imbalance. What's supposed to be white looks more like light pink. I think I might need to lower the red laser's current setting a little. The beam is also wider than the green and blue ones, so you get these discolored edges. One major innovation of this project was animation support. It's really satisfying to take an animated GIF and turn it into a laser projection in just a few minutes. Of course, the big limitation is the color range. It works best with simple designs that have a limited color palette and sharp edges. Cartoons, logos, and pixel art deliver the best results. Photos, like this one of me, can be converted, but they really don't look great.
Now, I know what you're probably waiting for. Longer range tests. So let's take this thing outside.
Here, we're at a distance of about 50 feet, projecting on the side of a house. Night filming meant I had to bump the ISO up on the camera, which added a lot of grain to the video. But in person, the image was fairly sharp and bright. I also decided to have some fun and spray some water here in front of the beam, which produced a really awesome visual effect. But let's push things a little bit further. Here's what it looks like at a distance of almost 100 feet, projected onto a brick wall. Now, I realize that the video quality is kind of bad here, but the image was still completely visible to the eye, though noticeably dimmer at this range. It was actually kind of hard for me to find a flat surface more than 100 feet away, and I didn't want to be rude or do anything dangerous by projecting it on neighbors' houses or businesses. But I did shine it up onto some trees over 200 feet away, and it was still quite visible to the naked eye.
So, what's the verdict?
Power-wise, it's decent, but a more powerful laser module would improve the range. Of course, that would mean redesigning the electronics to handle more power and heat dissipation. The resolution certainly isn't impressing anyone, but it's an order of magnitude better than the first device that I built. I also think that it could be improved. I would just have to find a much faster motor and a more accurate timing system. Battery life seems really good. It's a 4 amp hour battery, so no surprise there. I don't like running it for more than 30 minutes at a time though, because the bottom plate gets pretty warm, indicating that things are getting toasty inside. Maybe a cooling fan would have been a good idea.
Overall, I think it's a really cool and unique device. It has its limitations for sure, but as a concept, I think that it has a lot of potential.
If there's a commercial use, it would probably be projecting brand logos on buildings, though there might be some safety and legal concerns with that.
Now, there's a lot of things that I skimmed over in order to keep this video a reasonable length. In fact, I worked on this for over 6 months. But if you have any questions about this project, feel free to leave them in the comments section. I really do try to read all of them and answer what I can. If you've made it this far, I just want to say a huge thank you to everybody who has liked the videos, subscribed, commented, all that stuff. It really helps out the channel with the algorithm, and I appreciate you. Thanks for watching.